Okay, so vertical shifts, taking our kind of initial start function, and we are shifting it up or down. If we are moving our function up or down, what are we changing about the function? We're changing, well, not just the y-intercept, we're just changing the y values in general, all right? So this is a shift that very, very much we are really only going to see, not really affecting the x values, only really affecting the y values. In terms of our function, what do the y values kind of correlate to? Like the x's represent the, yeah, it's like f of x. It's the outputs to our function. If the x's are the inputs for our function, then the y's, the f of x, these are going to be the outputs of our function. So let's say we're looking at some kind of graph. X, y. And we'll say that our parent function for this, this f of x, will be equal to x squared. All right, so kind of our standard quadratic. I'm not going to be too worried about these specifics here. But man, I struggle with that on the iPad. Something like, holy, we're just not going to be able to create something that I'm happy with, so we'll just have to do our best. So kind of just that very, very standard sort of quadratic. If I wanted to shift this quadratic, if I wanted to shift my function up by 2, what do I do to all of my outputs? Increase them by 2. In other words, I would take f of x, and I would just take whatever output is normally at this value of x and add 2. And what do we get? We get the exact same shape, but instead of kind of centered around 0, we will see it shifted up by 2. Right. It looks a little bit smaller. It's not actually smaller. That's just struggling. Okay. Now, of course, that's lovely. We can shift something up by 2. That's really cool. We kind of want to have a little bit more flexibility than just moving something up by 2. So rather than saying that we are going to look at f of x plus 2, let's instead maybe say that we want to look at f of x plus k, where k represents how far up we are going to be shifting. Of course, if we are shifting down, k is going to be some kind of negative value. And so we would end up with some kind of function here. We'll call it f prime of x, which is x squared plus k. We are just taking that output, whatever we would have gotten, and just tacking on some extra amount that we're going to be pushed up. Okay. Vertical shifts, these are kind of the really, really nice ones. You add 2 to your function height increases by 2. Okay. Sure. Not too bad. Another way that I kind of really like to think about this is, I think, something that is maybe a little bit less obvious, maybe a little bit less intuitive. And that is that we are kind of taking the point. Thank you. We're kind of taking the point, the origin, 0, 0, and we're shifting that origin to the point 0, k. Now, this isn't just the origin. This is actually any point on my graph. I can think of shifting it by k up. The reason why I want to highlight this idea of we are shifting the origin in particular is because oftentimes our parent function, and we'll see this a little bit as we start to work in Unit 2, oftentimes our parent function maybe isn't defined at 0, but maybe it has some really interesting properties at 0. Maybe we have a horizontal asymptote that cuts through the origin. We have a vertical asymptote that cuts through the origin. And so even though our function isn't defined at this particular value, it can still be very useful to track where the origin is moving. That is to say that these kind of vertical shifts don't just affect the points on my graph. They affect everything in this kind of XY plane. They move asymptotes. They move like points that don't even really matter to what is going on. They move holes. It is everything that is kind of being subject to this plus K, which we're actually going to see is really, really nice. It means that we have a lot that we can kind of gain if we can really understand what this transformation is kind of trying to do. All right. So vertical shifts, we tack on some kind of plus amount, that's the extra amount that we shift up. Okay, those are the nice ones. Those are, or that one's the nice one. That one's not too bad. The significantly less nice one is going to be a horizontal shift. If a vertical shift is moving us up or down, what is a horizontal shift going to do? Move to the right or the left. So moving some kind of parent function. We'll say to the right or left. All right. If we are shifting to the right or the left, what kind of values would I expect to change? These are going to be my x values. So if shifting up or down changes my y values, instead what we are going to be seeing here is a transformation on not the outputs of my function, but the inputs of my function. This is always going to be happening on the inside to my x. This is like a transformation that happens before, and then my function kind of takes that information and runs with it. Okay, so kind of using this framework, kind of what we did, how would I communicate that I want to take my parent function and shift it, we'll say, 2 places to the right? How would I do this? Okay, so I think a really good way to kind of start is to think of this as f of x plus 2, where that plus 2 is kind of happening to the inside. Is this what's going to end up actually being the case? No. Horizontal shifts don't play nice. All right. What's kind of the tricky thing that we have to remember about horizontal shifts? It's the negative version of the direction that we're trying to send it. So I think this is a very, very good intuitive kind of guess as to what would happen. But you're probably just kind of told this as a rule to memorize, that if you want to go to the right, you have to subtract, and if you want to go to the left, you have to add. So for in actuality, what we would see is that this is going to be -2. Okay, I think that that's very unsatisfying, though, as an explanation of like, oh, well, if it's happening on the inside, you just do the opposite. I think that that is malarkey. I don't think that that is very helpful for actually understanding why does this create a shift in the opposite direction that we expect. Right. Think of what this -2 is doing is as whatever we're plugging into our function, it is being reduced by 2. So if I wanted to plug in 0, if I tried to plug in 0, what am I actually plugging in? Well, I'm actually going to end up plugging in -2. If I want to plug in 4, or if I try to plug in 4, what I'm actually going to plug in is 2. Everything I try to plug in gets reduced by 2. If I want to fight that, if I want to readjust myself, if I'm trying to figure out what's going on at f of 4, what do I have to plug in? If plugging in 4 would tell me what's going on at f of 2, what would I need to plug into x in order to figure out what's happening at f of 4? I'd need to plug in 6. If I want to know what's going on at f of 10. What do I need to plug in? Well, what have I done to fight against the fact that each of my inputs is getting reduced by 2? I've had to add 2 to all of my inputs. That is my shift to the right. I'm shifting to the right to balance the fact that my function is dragging me to the left. This -2 is throwing off all of our inputs. It's reducing them all by 2. If we want to know what's actually going on, what are the y values that we expect to see, we need to forcibly adjust, drag our function to the right to offset the fact that this -2 is going on in the machine. Right? So we're fighting against what's happening on the inside of our function here. And so what we have, again, to kind of keep this generic, is that if I want to shift in some kind of direction to the right, we're looking at f of x minus h, this kind of generic h here, where if I want to plug in a value, I need h more than what I initially would be plugging into my parent function in order to actually see the output that I want to see. So we're being dragged to the left, and so we pull ourselves to the right. So the horizontal shift, a little bit mean. It does the opposite of what it looks like it does. You can think of this as we need to fight against what's happening on the inside. We need to counter whatever this is. So what we see here, this function, it's pulling us to the left by 2. We need to shift to the 2 in the opposite direction, 2 to the right. Whereas the output, super easy. The output just happens, and then we're just moving up by 2. Okay, exact same idea. We could still think of what is happening to the origin here. In this case, we are taking the origin 0, 0, and really just kind of sliding it in that x direction, moving it to h, 0, right? Just shifting it along that x-axis. But we can do both at the same time. And so we might say that our function, this like complicated f of x minus h plus k, is a function that takes the origin 0, 0 and moves it to our new point h, k. We're going to look at what's called vertex form for quadratics here in a little bit. And what we're going to see is that vertex form looks a whole lot like this. And what it does is it takes the origin, which is the vertex of our parent function quadratic, and it moves it to h, So exact same logic here. We are taking this kind of point and shifting it. Which again, we're doing it to every single point. The origin is just kind of a nice focal point to kind of close in on and see what's happening. But it is happening everywhere at the same time. All right. So let's take a look at an example here. Before we do though, any questions on our vertical horizontal shifts? Vertical plays nice, exactly what you'd expect. Adding shifts you up, subtracting shifts you down. Horizontal plays mean, you have to fight against horizontal. So if I'm being pulled to the left, I have to drag myself to the right. Let's take a look at example 1 here. In this case, we are given a parent function. That parent function is 1 over x squared, and the goal is to write a transformed function using these kind of descriptors, using these shifts. So let's start just kind of generically. Looking at 1a, I'm told that I want to look at a function that has been shifted down by 4 and to the right by 3. What is down by 4 going to look like? -4 to the inside or the outside of our function? to the outside of our function. And then what is to the right by 3 going to look like? Minus 3 to the inside of our function. So we're thinking that we go from f of x to f of x minus 3, and then on the outside, minus 4. Again, shifting to the right by 3, we're fighting off the fact that there's a minus 3 kind of in that machinery. All right. This is really, really good for just kind of like if I gave you a generic function, we actually have a specific function to plug into though. So in this case, our f is 1 over x squared. And so everywhere I see an x, replacing it with an x minus 3.
Just please pardon this interruption. I just want to say good afternoon to every single dragon in this dragon family all throughout the building. Hope that you all had a marvelous Monday. Students, as we get ready for dismissal at 2:30, I do want to let you know now that everyone knows their bus numbers, where the buses are typically located, how to get there, how to read to see exactly where your bus is situated. Buses will leave this campus every day at 2:37 p.m. Let me say that again, that's 2:37 p.m. We have to get buses to the middle school that's waiting on us after they finish dropping you guys off, and then after that we move to they move on to the elementary school. Please do not play around when you leave out of your 5th period class. Find your bus number, go straight to it. Find your bus, go straight to it. Buses will be leaving at 2:37. This is not a good time like you guys have been doing in the past couple of days, giving each other a high five, kicking it, and having a great time. Yes, we will be leaving on time. Have a great day, everyone.
No high fives on the way to buses. That is strictly illegal. That's like instant ISS. If I see anyone high-fiving, absolutely despicable behavior. All right. Great. So f of x minus 3, that is taking our x, replacing it with an x minus 3. So everywhere we see an x, we write x minus 3 instead. And then at the end, tacked on to the very kind of final piece of our function, this minus 4. All right, questions with A here. All right, I'm going to give you guys a couple minutes. Take a stab at B and C as well. Yeah. So normally you'd be correct. Right would normally be positive, left would be negative. Horizontal shifts are a little bit weird because they work the opposite way that you would expect them to work. Yeah, so when we see right and we think positive, think opposite, it's going to end up being negative. The way to think about it is we have to fight against what's going on the inside. And the way we do that to counterbalance the fact that there's a minus 3 on the inside, we have to shift all of our x's up by 3. That's just if our parent function is this. So like this would be correct for any function that is shifted in this way. But I gave you a specific function, and this specific function is the 1 over x squared. Yeah. So think of that like first line. Yes, let me get you. Yeah. Yeah, so click on access code. And then Yours. Yes. If you want to take a picture, it is this one right here. Do you have another question? Yeah, so that's just the. Perfect. Super good. This is good. Just up the square there. And then you want to plug it into the specific channel. Perfect. That's good. So when you are doing the shifted up by 2, that up is going to be on the outside of which axis. To the left by 4 is going to be on the inside. So it would be x in parentheses, x plus 4, and then on the outside. Oh, okay, you're good. Perfect. This is good. Oh, you're good. Awesome. So you're fine.